Hello, I'm Jan and I'll be presenting our paper named Locally Checkable Problems in Rooted Trees. This is a joint work with Alkida Balio, Sebastian Brandt, Denis Olivetti, Jukka Suomela and Alexander Tereshenko. In this work, we show what are the possible round complexities of locally checkable labeling problems in rooted trees and present an algorithm that determines in which class any given LCL problem resides. The model of computing is both randomized and deterministic local or congest model. In these models, input graph describes also the communication network. Each node has a unique identifier of the order of log n bits, and in each step, nodes can exchange arbitrarily long messages with their neighbors, in case of the local model, and log n bit messages in case of the congest model. The problem class that we focus on are locally checkable labeling problems. These are problems whose solution can be locally checked. Examples of such problems are graph coloring, finding consistent orientation, or maximal matching. And finally, underlying graphs where we want to solve such problems are rooted regular trees where each node has either 0 or k children, where k is some integer. Moving on to results. Let me tell you what are our contributions. First, we show various gap results and prove that all LCL problems have to be solvable in either constant time, log star time, log n time, or polynomial time. Second, we prove that for regular rooted trees, there is no benefit of having large messages, and moreover that randomness doesn't help. This means that on rooted regular trees, all four models are equivalent to each other. And most importantly, we provide a centralized algorithm that can automatically classify asymptotic complexity of any LCL problem. The running time of the classifier is exponential in worst case, but it is nevertheless practical. To put things into perspective, let's look at the landscape of LCL problems in various graph classes. When we look into paths and cycles, the only possible complexities are constant time, log star time, and global, as shown in a seminal paper by Nauer and Stockmeyer. Deciding complexity of a problem can be done in polynomial time, shown by Chang, Me, and Suomela. In regular rooted trees, the situation is a bit more involved as we have additional log n complexity class and a whole range of polynomial complexities. For general trees, randomness starts to help, so we have a complexity class log n, and for general graphs, the range of complexity is even richer. But we also know that in general graphs, we cannot decide a complexity of a given problem. Moving on to a technical part of the paper, our main tool are certificates for constant time, log star time, and log n time solvability. In the paper, we introduce this notion and show that any problem has respective certificate of solvability. Before describing the certificates, let me motivate our work with one interesting observation. This will be called complexity of computing maximal independent set. Computing maximal independent set is a well-known symmetry breaking problem. We can encode it in our formalism as seen on the slide with two auxiliary labels. One would guess that the complexity of such problem has to be log star, but in the rooted trees it is not the case. In rooted trees, one can compute MIS in constant time. An algorithm for solving MIS will have 4 rounds, so let me explain it how it works. We assume that we have some port numbering for the children, so we can refer to the first and the second child. As a first step, each node looks 4 steps upwards and colors itself with the port number sequence. Then, we just apply fixed transformation from the color to the output label, and we are done. The nodes with label 1 will form a maximal independent set. So now we know how to solve MIS, but in order to address all constant time problems, a general notion of constant time certificate is needed. The certificate of constant time solvability consists of 2 parts, a set of balanced trees and a special repeating configuration. The balanced trees have identical bottom layer and all possible labels on the root. What you can see on the right is a certificate for constant time solvability for MIS. Let me show you how to use the certificate to solve a problem in constant number of rounds. As a first step, each node again looks upwards for a constant number of steps and colors itself with the port number sequence. Then we identify colors that form a periodic string with sufficiently short period, like 111 or 1212. Observe that they form paths. In the paper, we moreover prove that they are far apart from each other. These paths will be labeled by a special repeating configurations as follows. Other colors can be used as locally unique identifiers in each component. On a high level, we use colors to split the components in constant size subtrees, and then we label the subtrees with the help of the certificate. We put the certificate labels in the middle, then we greedily fill down the rest of the trees, and we finally fill the top using the certificate. Before conclusion, let me quickly show you the online version of the classifier that is freely usable for anyone. The code that is classifying problems is now part of LCL classifier developed by Tereshchenko in 2021. It is a web interface, so it is very convenient and doesn't require any installation. It supports multiple classifiers, so the naming is slightly different. Configurations become active configurations, and passive configurations will be just an identity map. I have prepared an example to show you how it works. There are 6 active configurations for the MIS problems, and they should be read as follows. For example, the first 3 configurations says that a node labeled Y1 can have children labeled by either AA, AB, or BB. Then a node labeled by A has to have 2 children labeled by B, and a label B can have children either B1 or 11. To see the round complexity, we just type the configuration, then press find to get the both upper and lower bounds of the problem. And here we see that indeed such problem is constant time solvable. Now we have proceeded to an end, so let me summarize what we have done. We showed what are the possible round complexities of locally checkable labeling problems in rooted trees, and presented an algorithm that determines in which class any given LCL problem resides. This is end of my video, and I'll be happy to answer all questions during the PODC session. Bye!